Welcome. In the last lecture we started looking at models for activity coefficients for binary systems consisting of two components, and we said we would limit ourselves to binary systems in this particular course. We looked at the Margulis model and we found expressions for gamma 1 and gamma 2. We started looking at the Redlich-Quistem model, which is GE by RT equals B x1 x2, where B is a constant for the particular system. And what was started out in class and left as homework was that to derive the expressions for ln gamma 1 and ln gamma 2 for the Redlich-Quistem model using the same procedure as we did for the Margulis model. Hopefully you would have obtained these particular expressions. I will start this again. Yes, ln gamma 1 equals a simple Bx2 squared, equation 437, and ln gamma 2 equals Bx1 squared, equation 438. Hopefully you would have gotten this, and the same way that we did then by analysis of the Margulis model at infinite dilutions, you know that one of the terms will get to, one of the mole fractions will go to 1, and as a consequence the other mole fraction will go to 0. Ln gamma 1 infinity equals ln gamma 2 infinity, that is B, which is the constant B for which would be the constant in the Redlich-Quistem model. There is another model again for binary systems to find activity coefficients, which is called the Van Laar model. Of course, the model is for GE by RT. Van Laar model says that GE by RT equals A12 dash A21 dash divided by A12 dash x1 plus A21 dash times x2. This is the Van Laar model, equation 439, where A12 dash and A21 dash are system dependent constants. They are particular values for a given system, and by using the same procedure, I am not going to give you extra time in class this time. Please take this as homework and do this, maybe it will come back as one of the exercise problems too. By using a similar procedure as we did for the Margulis and the Redlich-Quistem models, if we find the expressions for activity coefficients, they would turn out to be ln gamma 1 equals A12 dash times 1 by the square of, see this is to the power of minus 2, therefore 1 by the square of 1 plus A12 dash x1 divided by A21 dash x2. Let us call this equation 440, and ln gamma 2 would be A21 dash times 1 by square of 1 plus A21 dash x2 divided by A12 dash x1. We will call this equation 441. And at infinite dilutions, as we did earlier, when x1 tends to 0 or x2 tends to 1, we have ln gamma 1 infinity equals A12, quite easy to see. You put in x1 equals 0, irrespective of x2 this term vanishes, and therefore this term just becomes 1, and therefore ln of gamma 1 at infinite conditions we are left with A12 dash constant alone. And similarly, if you substitute x2 equals 0 here, this term vanishes completely and this term reduces to 1, and therefore ln gamma 2 infinity is nothing but A21 dash. Okay, so we have seen three models: the Margulis model, the Redlich-Quistem model, and the Van Laar model. We look at another model, which is Wilson model, which has some backing in theory. It is based on something called a local composition concept. We will not get into the details of what the concept is and so on. It is slightly beyond the scope of this particular course, but you need to know that this has some grounding in theory. The local composition is postulated to account for the short range order and the non-random molecular orientations. If you can imagine that, that is fine. If you do not, that is also fine. That result from differences in molecular size and intermolecular forces. This is some general way, general basis for the Wilson model. You can look at this. If you understand that, it is okay. And as we mentioned, this model has a better grounding in molecular theory of solutions. And not just this model, there are so many different models that are available in the literature. All these were developed a long time back, many decades ago. Some of them are NRTL, UniQuack, UniFac, and many of these require computer programming to get at solutions. We will not get into the theories. I just wanted to mention the theories so that you will know the names when you come across them later, and you can easily pick them up once you know the basis, GE by RT and so on and so forth. You can pick them up and then use them for estimating activity coefficients. So as long as you know that there are models called NRTL, UniQuack, UniFac, and probably others too, which can be used for estimating activity coefficients, that is good enough from this particular course. But for now, let us look at the details of the Wilson model. The Wilson model says that GE by RT, it has to be a model for GE by RT, equals minus x1 times ln of x1 plus x2 times gamma 1 2 minus x2 times ln of x2 plus x1 times gamma 2 1, and we call this equation 442. This is the model. Gamma 1 2 and gamma 2 1 are the constants, the Wilson model constants or Wilson constants for a particular system, and you could do the same things that we did with the other models, the Margulet, Redlich-Kuster, Van Laar and so on, to get at expressions for gamma 1 and gamma 2. If you do that, to recall, you need to differentiate it with respect to n1 with constant Tp n2, and then recombine the terms with the recognition that x1 plus x2 equals 1. So we do that, ln gamma 1 will turn out to be minus ln of x1 plus x2 times gamma 1 2 plus x2 times gamma 1 2 divided by x1 plus x2 times gamma 1 2 minus gamma 2 1 divided by x2 plus x1 times gamma 2 1. This is equation 443, and ln gamma 2 is a similar expression. There will be some changes here, there will be no changes here, minus ln of x2 plus x1 times gamma 2 1 minus x1 times gamma 1 2 x1 plus x2 times gamma 1 2 minus of gamma 2 1 divided by x2 plus x1 times gamma 2 1. We will call this equation 444. At infinite dilutions, we will get ln gamma 1, the x1 tending to 1 and x2 tending to 0, x2 tends to 0, this whole term will drop out, x1 is tending to 1, therefore we will get minus ln of gamma 1 2, I think it is the other way around, plus 1 minus gamma 2 1, and ln of gamma 2 infinity equals minus ln of gamma 2 1 plus 1 minus gamma 1 2. Okay. Just by substituting one or the other, x1 tends to 1 and x2 tends to 0, or x2 tends to 1 and x1 tends to 0. Okay, I think we have seen enough models for the GE by RT, and therefore for estimating gamma 1 and gamma 2. It is time to do an example, and we will finish up this module with this example of estimating module. Okay. The example is as follows. It is a straightforward example. Of course, I am going to give you time to work it out. Isopropanol, which we saw in the earlier chapter, is a substance with many biological applications and our very favorite substance, is purified through distillation. To design the distillation process for purifying isopropanol, the activity coefficients need to be used. Compute and compare the activity coefficients for an isopropanol water system with mole fraction of isopropanol being 30% using the following data taken from the literature. The Van Laar constants are given. A12 dash equals 1.04792 and A21 dash equals 0.49179, and the Wilson constants gamma 1 2 is 0.10714 and gamma 2 1 equals 0.64506. These have been taken from the literature, the Journal of Chemical Engineering Data. If you look at the notes, the reference will be there, and what I will do is give you some time to think about it, and then should I give you some hints? I think it is a reasonably straightforward thing. Yeah, it is mere substitution. So think about it for 5 minutes and then take the next about 20 minutes, a total of about 25 minutes to work this out, because you need to work out numbers and long calculations and so on and so forth. So take about 5 minutes for thinking, getting to how to go about doing it, and then doing it actually, and then we will meet after about 25 minutes. Go ahead please. Okay, you would have had time to think about this. What we are looking at is isopropanol, and what we need to do is compute and compare the activity coefficients using two models that we have covered so far, and it is quite evident that we have models for ln gamma 1, ln gamma 2, the expressions for them, which we derived from the various models, which are expressions for GE by RT. And therefore, if you substitute the constants that are given here with the mole fraction of isopropanol being 30%, and it is an isopropanol water system, therefore the mole fraction of water needs to be 70%. If we do that for the Van Laar model, gamma 1, ln gamma 1 was this, therefore gamma 1 would be exponential of A12 dash times 1 plus A12 x1 by A21 dash x2 the whole power minus 2. If you substitute the values which have been given, it turns out to be exponential of 1.04792 for A12 dash times 1 plus 1.04792 times 0.3, which is the mole fraction of isopropanol in the binary solution, divided by 0.49179, which is the constant A21 dash in this model, Van Laar model, times the mole fraction of water 0.7, 1 for isopropanol, 2 for water. If you do the calculations, you should get 1.331. Okay, so this is gamma 1 for isopropanol in this particular binary system, and gamma 2 a similar expression that we have already seen, which becomes exponential of A21 dash times 1 plus A21 dash x2 divided by A12 dash x1 the whole power minus 2, and substituting the values 0.49179 for A21 dash and A 1.04792 for A12 dash, 0.7 for x2 and 0.3 for x1, and doing the calculations on a calculator you will get 1.119 for gamma 2. Okay. What I would like you to note, okay, we will note that a little later. Now we were asked to do that for the Wilson model and compare the two. Therefore, if you look at the Wilson model expression, which is a slightly longer expression, gamma 1 equals exponential of minus ln of x1 plus x2 times gamma 1 2 plus x2 times gamma 1 2 divided by x1 plus x2 gamma 1 2 minus gamma 2 1 divided by x2 plus x1 times gamma 2 1, as you can directly pick from whatever was given in your notes earlier, excuse me. And substituting the values, in this case 0.3 and 0.7 remain the same as mole fractions of x1 and x2 isopropanol and water respectively, whereas gamma 1 2 is 0.10714 and gamma 2 1 is 0.64506. That is what, this is what was given in the problem statement itself. If you substitute the various values here, which you would have done in the time that was given, you would get gamma 1 equals 1.965, and a similar exercise for gamma 2 would yield gamma 2 equals 1.276. Now, look at this gamma 2 value. From the Wilson model it is 1.276, and from the Van Laar model it is 1.119. There is a variation, and that is the reason for coming up with different models for different systems. This just gives you an idea of the variation that you can expect. The gamma 1 also has a variation. In the case of Van Laar it is 1.331 that we got, and in the case of Wilson it is 1.965. Okay. You need to be aware of this, there is nothing wrong with this. This is the various constants were taken from experimental data. So there is, this is the kind of variation that you would expect, and that was the reason for coming up with better and better models. We already talked about NRTL, UniQuack, UniFac and so on. Okay, I think we need to stop here in this class and see you in the next class.